record is in progress. Okay. So that is one of the examples. Another example you can see if you have a car also, there's a shaft which is linked with the engine and also the shaft, right? To propel your uh, what is it? The wheels. Okay. So it can transmit the torque uh, to the wheels. Okay. So actually the generator, the power is going to be the same, equal, but it's opposite. Okay. Okay. So for this chapter, okay. So the topic we will focus on the torsions, stress in the elastic range, right? Solid and hollow shaft is going to be different. How to calculate the deformation, especially the deformations, right? So hollow and solid and also different materials is going to be different. Okay. And shaft subjected to multiple torques. Okay, multiple twists. Shaft deformation, angle of twist. This is the important. Similarly, like a previous chapter, we have to calculate the deformation, but this one is based on the angles. The previous chapter, we whether your shaft or your what is it, the truss is going to be compressed or tension, right? But this one is more to like it's twist. Okay, so we have to calculate the angles, the value of the angle. Okay. So I hope that you are able to define what is a torque, twisting couple, and also torsion. Twisting couple is the same force we apply but different directions. Okay, like how to say? Similarly, like upward and downward, right? Okay, but this one is maybe clockwise and anti-clockwise. That one is twisting couple. Okay, and then derive elastic torsion formulas. Okay, and then formula for the angle of twist. This one is important, and also calculate shear stress and angle of twist, circular shaft, solid, hollow, and step under one of the multiple torque. But I think we will cover also about the power. Okay, just a small part. Uh, I think I just give the example about the power transmissions. Okay, at the end of this chapter. Because this is important for the engines. Okay, the move the what is it? How to calculate the torsion deformation based on the power. Okay, okay. But I think for the final, I didn't include power. I think. Eh, I don't remember. Test. For no. Okay. I think so. This chapter is the one who prepare is. Yeah, I think so. I'm the one who prepared this one. This chapter 2, 3. Yes, I prepared this one. I don't think the power is included. I'm still not remember included or not. Okay, but it's okay lah. Uh, okay. So if you look at here, asal tak jalan. Okay. Torque or torsion is a moment that twists a member about its longitudinal axis. Okay, meaning that whether clockwise or anti-clockwise. Okay, is a moment. Okay, should be the distance and also force. Okay, not only force. Okay, it should be a distance. Torsion is a primary concern in the design of the axles and drive shaft, right? Transmission shaft used in vehicles. Okay, like your motorbike, car, what else? Ship, all those vehicles. Okay, turbines and also machinery. Okay, so we actually interested in the stress and strain of circular shaft, subjected to torsion or twist. Okay, so like if you use a auger to, you know auger, right? Auger to, what is it, for the soil. Okay, dia macam like a spring, right? Untuk apa tu? Untuk buat tebuk kan? Okay. So that is another one of the concept of the torsions lah. Okay. So if you look at here that for the torsion, the torsional stress, and this one is the auger. This one auger. Okay. The torsional stress and angle of twist of this soil auger depend upon the output of the machine turning, the bead, as well as the resistance of the soil in contact with the shaft. Okay. Actually, if you use this auger, okay, to how to say, um, actually there's a deformation occur, especially there, of course there is a deformation, but it's gonna be not really visible. Okay, it's gonna be written or something like maybe the angle of twist is only how many percent, 0.0 something okay, but it's not for this auger is not going to be failure. Okay, so that is important to calculate the minimum diameter that we have to use to design this auger also. Okay, and the power output that we have to set. Okay. Okay, so the application of the torsions or the torsions, okay. For examples like a turbine, right? If you look at here that turbine exert a torque T on the shaft, okay. This one, okay. Where's the turbine? Is give a power, exert torque, okay. It's gonna be rotate. This one is counterclockwise, right? And this shaft actually is transmit the torque to the generator. This one, okay. So generator creates an equal and opposite torque. So meaning that, so if shaft is transmit to this side, the turbine exert torque to the clockwise, the shaft will be opposite, because this one is with this one is gonna be cancelled out, right? It's gonna be opposite, okay, but the power is equal, okay. So it's important, okay. Like you open the, what is it, uh cap, the bottle cap, right? There's a twist also there, right? Okay, something like that. Okay, so let's see the torsional deformation of the circular shaft. That one is the deflections. So if you look at here, that if the angles of rotation is small, right? Okay, the length of the shaft and its radius will remain unchanged. Okay, so it's very small. So your shaft is not failure. Okay, so this is the deformation before deformation, and this one is after deformation. So we can see here there's a red, what is it, how to say, there's the angle of twist. Okay, where's the image? This one, sorry. So this one, you to this direction. Okay, the circles remain circular. Okay, so this is a remain straight. But if the rotation is bigger, so it's going to be changed lah, the radius. Okay. Okay. Okay, this is for the circular shaft. How about non-circular? Non-circular is meaning that is not round shape. Okay, not round shape. Okay, the cross sections non-shaft do not remain plane. Also meaning that like a rectangle, right? Or the square. Okay, like cubic type. So that is not the same. Okay, the radius. Okay, look at here that, and this one. This is a circular shaft, same. Okay, after torsion. Okay, the angle of twist increase as x increase. Okay, meaning that x is the length lah of this one. Definitely, if you increase the length, is the angle of twist are going to be increased lah. Okay, lagi senang kita nak deform kan. Okay, okay. So this one in term of non-circular, this is what I already explained. Okay. By contrast, cross section of non-circular shaft do not remain plane. This one. Okay. So if you look at here is a before undeformed, okay, before deformations, but after deformations, if you look at here, this will become bulk and also warp. Okay. So it's not same the radius. Okay. It's not remain the same. We compare with the previous one, right? This one. Okay. Radial lines remain straight, right? But this one radial line is not straight because it's follow uh, the shape of the shaft, right? Because this is the shape is a square, right? Okay, rectangles. Okay, so it's not remain the same. Okay, so how can we calculate the torsion formula? Okay, so and also shear stress lah. Okay, of course, we have to use Hooke's law. Okay, that is important. Okay. So how to calculate? Okay, if you look at here for the elastic torsion formula, the material is linear elastic. Okay, we apply Hooke's law. The linear variation in shear strains leads to a corresponding linear variation in shear stress. along any radial line of the. So meaning that this one is a, if you have, but we have to consider whether clockwise or counterclockwise depending on the, how to say, thumb rule lah. Okay, this is a thumb rule. So we can see here, this is a counterclockwise. Okay, okay. Whether clockwise or anti-clockwise, later I will explain. Positive is clockwise or not, negative clockwise or not. Okay, so this is a maximum shear stress. Okay, okay, and tau max, right? This is tau max, but sometimes we use tau lah. If any position, for any position we use tau, but if maximum this here, this is the maximum. Tau is any position here, here, here. Okay, but at the end of the, how to say, outer of the, almost outer of the shaft, so we call it as a T max lah, tau max. Okay, that is the maximum shear stress that we can calculate lah. Okay, because the value is going to be different depending on the angle. Okay, this one. Okay, so resultant internal torque, this one T, if you apply this one, if you twist to this side, to the counterclockwise, right, and then polar moment of inertia of cross sectional area. So polar moments J is actually is a different between a tubular and also solid. Okay, tubular and solid. Solid is there's a no hole. Okay, meaning that is there's a hole here for the tubular. Right. So it's depending on the outer diameter, outer radius outer radius and also inner radius. This one is tubular. But for the solid shaft is only one radius. Is we just denote as a C. Okay. For the C lah, outer radius. And intermediate distance rho, or we use R lah. Similarly, actually rho is any distance, like T we use rho, but C is the we use maximum. Okay, this is actually we use R. Sometimes we use R, right? R1 or R2. Okay, for tubular. Okay, but this one we define using C and also rho. If you look at here, this is a rho, right? For any distance from the center of the circular shaft. Okay, so meaning that if you have a tubular, if I still remember the equation, okay, for the solid shaft, okay, so J, this one, right? How to determine J? This is our equation or symbol that we have to determine first, because if from the shaft, okay, circular shaft, we can know this torsion and also rho, okay, but the problem we have to determine this one. So for the solid shaft, okay, J is equal to half pi C4 lah, C power 4. Okay, so C here, the distance from the center, C lah. Okay, so meaning that if you have a solid shaft, something like this. Okay, this is a T max lah. A tau max, T max lah. Okay, this is a C, the distance, the radius distance. Okay, so this is a center lah. Okay, okay, so that is for the solid. How about for the tubular? Okay, the cross section is going to be because there's a hole inside here, right? So there's a hole. So there's a hole here. So C, this one is going to be C1, C2 lah. Tak boleh tukar. This one C2, that C1. So meaning that this one is a C2 minus C1. Okay. Okay. So this is the how to calculate J. Okay. This one is the equations. Okay, sorry. Okay. So this is the equation to determine J. If you look at here, this is C1 and so C2. This is T minimum. Meaning that if T minimum is around here, okay, and T max is here. Okay, but this is in terms of trigonometry, the maximum. Okay, tau, sorry, not T. Okay, so the one that the equation that you have to remember is this one. This is the equation that you have to know how to use. Okay, okay. So let's see the example. Okay, for the torsions. This one is a hollow and solid shaft. Okay, if you look at here that shaft BC is hollow. Okay, this one, the shaft BC. This one hollow. Inner and outer, they have 90 millimeter and 120 millimeter respectively. Right. Shaft AB and CD solid. Okay. AB and CD solid. Okay. Of diameter D. For the loading shown, determine the maximum and minimum shearing stress in shaft BC. Okay. So if you look at here, minimum and maximum, right? So this is hollow. So when it's hollow, you have to use a equation that J is equal to half pi C2 minus C1. Right. Power 4. This one, J. Okay, so we can determine tau min and also tau max. If I still remember. Okay. Okay. And then the required diameter D of shaft AB and CD, this one. Allowable shearing stress in this shaft is 16. So meaning that this one is tau. Okay. Allowable stress. Okay. Tau, not T, sorry. Tau. Okay. It's tau always. I see the different symbol. Okay. So how we have to do this? How can we solve this problem? Okay. Uh, please remember, please draw free body diagram. Okay, this is procedure by using a method of section. Okay, method of section method. Okay, method section method of section. Okay. So cut section through shaft AB, BC and perform static equilibriums. Okay, apply elastic torsion formula. Elastic formula is just now this one tau. Okay. And then what else? You have to given allowable shearing stress and apply torque invert the elastic torsion formula to find it. Okay, so if you look at here that because we want to determine the what is it, the stress, right? Shearing stress at point between B to C. So we can start from this side or we can start from this side. Any side is possible. Okay, so you have to cut if these examples, they start from the left side A to B, right? So my suggestion is how to draw this one. You can draw the original picture first and then cut just like a previous one I show you. Okay, this one they have an original picture. Okay, so they cut from this side and then they determine TAB, the internal force. Okay, so we can get TAB is 6 kilonewton meter lah. Okay, so if you look at here, okay, so this is similar to TCD. Okay, so if you calculate from the right side, okay, why is similar to CD? Because this one also 6 kilonewton. Okay, this one 6 kilonewton. Meaning that if you calculate from this side also, because this direction, right, similar 6 kilonewton, just the opposite. Okay. Okay, and then for the shaft BC, okay, since we determine already TAB, okay, TB, TA, right, okay, so we just determine TBC, so we can get 20 kilonewton. So method of section is important. I think for this chapter 1 and chapter 2, chapter 3, the method that always we use is method of section rather than method of join, because method of join is we can apply only for the truss, right? Rather than other shaft, okay, other members. Okay, so we get a 20 kilonewtons. Okay, and then we apply the elastic torsion formula. This is for shaft BC lah. Okay, if you look at here that see we already determines the shaft BC is 20 kilonewton. So just substitute just using the what is it the hollow shaft formula, substitute the value for inner and outer diameter. This one is we change to the diameter is 90, right? 90 and 120. So that is diameter. So we change to radius lah. So just divide it into two. Okay. So we can get this one. This one 120 diameter. This one is a 90 lah. So this one 120 millimeter, right? Divided by 2. Okay. Because C is the radius, not the diameter. Okay. So we can get 13.92 times 10 negative 6. Okay, substitute into tau max. Okay, so tau max is the outer one. Okay, that's why we use the 0.6. This is the outer, this side, this one, C2. Okay, so we can get tau max. For T minimums here, we use this one lah, the diameter. Okay, so we just using the ratio C1, C2 and tau max. So we can get 64.7. Okay. Okay. Is it clear? This one? Okay. So for B, what we have to do is to determine the diameter of D. Okay. Shaft AB and CD. So how can we determine this diameter? Is given the stress, shearing stress 65 megapascal. Okay. So since it's given, so you just calculate lah, back calculation. You substitute tau max with 65. Okay. So just determine the what is it? The diameter lah. Okay. That's determine the diameter. So we can get the diameter for shaft AB and CD. Actually, this one is the same. Okay. For shaft AB and the diameter is AB and CD is the same. CD. Okay, because the same if you look at here, the same, right? Left and right. The force is given. Okay, this one. This one. 6 kilonewton and also 6 kilonewton. Okay. Is it clear, this one? Before we move to example, I think for this chapter, the explanation is based on the example rather than theory. Okay. Is it clear? Clear, right? Before we move to the deformations, angle of twistor. Okay. Okay, let's see the example 2. Okay. For example 2, if you look at here that I think it's similar. The pipe shown has an inner diameter, okay, ID 80 millimeter, and outer diameter is 100 millimeter lah. Okay, its end is tightened against the support A using torque wrench B. Okay, this one wrench. Okay, actually, this one we call it as a moment couple. Okay, this one you push, this one you pull. This is what we call it a moment couple. So it can generate a moment. Okay, so this is what we call it a moment couple. Okay, so we have to determine the shear stress developed in the materials inner and outer. Okay, so it's given already, this one 80 Newton meter. Okay, this one we determined already, is given already the diameter. Okay, so we look at here that by using a torsion formula, right? So we just how to say, determine the T, because we don't know the T, right? Okay, it's given this one. this side and to this side, the moment couple. Okay. So by using a moment, okay, because mostly we use because this chapter is the concept is torsion. So we use a moment equation rather than total fx and total fy. We use this one is rarely we use for this chapter, okay, but we use more this one, okay, but sometimes it's necessary to use this other equation of equilibrium, EOE, okay. So similarly, by using a moment at here, okay, or any, I think this one 300 lah, this one times with 100%. So moment here, point here, okay, this point, this line, okay, 0.3 and 0.2. So we can get 40 meter. Okay, so we can get TC lah. Okay, so we have to calculate the radius. Okay, and then we calculate TC lah. Okay, TC2 and also TC1. Okay, by using the force that we already calculate. Okay, or moment. Okay, so this is the answer. Okay, for the sharing stress. Okay. I think this is the example, easiest example. I don't think explain this one. Okay. So this one, it stated that for this example, okay, determine the shear stress at point A and B. Okay. So if you look at here, this is around 20 millimeter from the center. Okay. And this is 35 millimeter from the center, meaning that this is a outer lah. See, this one is rho. Okay, we use symbol of rho because at any distance between outer and also center of the shaft. Okay, you have to remember when you have to use rho or C. Okay, rho is any distance between outer and also shaft. Okay, but C is only at the outer, at the maximum of the here, this side. Okay. Okay. So by using comparison, if you look at here that A and B, right? That's why we use rho here for point B, right? This one. This one we use a C here, outer. Okay, so we can see that this is the maximum. Okay, maximum shearing stress. Okay, we can apply. Okay, so if you look at here that definitely is a much lower, right? The value, this one at point B compared with point A. Okay, this one. Okay. YT is positive.
Doctor,
Yes.
just now the example 2.
Example 2.
For the moment, why the T is positive? Yeah.
This one.
Yes.
Wait.
At the
This one.
moment.
This one will be which one?
Yeah, this one, 40 Newton meter.
This one positive. Kalau you calculate.
How to determine the direction of the T?
This one. This one lah. This one, the answer lah. Huh? This one. This
Yes.
right? So if this one is gonna be clockwise, this one is clockwise, right? So negative. So negative 80 times 0.3 minus 80 times 0.2. Negative 40.
Okay.
So you bring to the right side positive 40 lah.
Okay.
Positive lah.
Okay.
Okay. So we just consider this one is because it's clockwise, right? Clockwise is negative. Previously we defined clockwise is total moment This one is positive, right? Equal to 0, counterclockwise. This one is going to be clockwise. Yes. This one clockwise. Sorry. This one, right? Okay. 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 It's 0. Betul lah. It's correct. Okay. 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 So I hope there's a fee sign rule actually later I will explain. But that one is after you get the final answer. Okay. Based on the fee signs rules. Either positive or negative. Okay. Ada example ke tak? Saya lupa. Let me check. Okay. So let's see angle of twist. Okay, clear, okay? How to determine that positive or negative. Okay, let's we calculate the angle of twist lah. Okay. Angle of twist, okay, similarly also like a previous chapter, but this one is more to angles. Okay, the previous we use at the members deform at the tension or compression, right? Okay. So but this one we use a symbol of phi. Okay, this one we call it a phi. Phi or pi. Okay, phi lah, I just call it phi. So the angle of twist, phi, and the maximum shearing strength. Okay, this is the equation that related. C, of course, this is the angle, and this one is the length lah. Okay, the longer of the length, the more is going to be deformed. Okay, for linear elastic materials, shear stress, shear strain, and also shear stress are rated by the Hooke's law. Similar. Okay. So for example, the previous one, this one is we use a G, but the previous we use E, right? Okay, we use E. Okay, so to calculate that phi, this one TL divided by JG lah. So T you have to determine by the torsion formula. Okay, this one length. J is the what is it? J is what? Yeah, just now with different with the between hollow and also tubular. Okay, that one is the what we call it polar moment inertia. Okay, but if we apply for different materials and also different diameter, okay, we have to use TILI, GI. So meaning that this one is a for different materials and also different cross-sectional areas. Okay, similar like a previous chapter. Okay. Okay. So if you look at here that angle of this of phi equal to TLJG. Okay. So just internal torque, length, polar moment, and also shear modulus, elastic G. So actually sign convention is determined by right hand rules. Okay. So whether positive or negative is your final answer is will be decided, will be determined by this one right hand rules. Okay, usually if you use if you how to say like your fist, right? This is thumb rules. Okay, you go inside or the thumb is go inside or upward or this one. Okay, whether is directed outward or inwards is determined whether it's positive or negative. Okay, so usually is positive is going to be directed to outward. Okay. Okay. This one is a phi science rule. Okay. So if you look at here, outward, right? This is your thumb. So it's going to be positive. It's to this side. Okay. This is to counterclockwise. We call it as counterclockwise, right? Okay. Counterclockwise. Okay. So this one. So please remember. So angle of twist will be positive provided that the thumb is directed outward. This one outward. From the shaft when the fingers curl to give a tendency for rotation. Okay, this one is positive lah. Okay. This is a counterclockwise. Generally, is counterclockwise, but rotate clockwise is gonna be inward. So when it's inward, it's gonna be clockwise. Okay, so inward to this direction. Okay, so your angle is gonna be this direction. Okay, so this is for the final answer. But before for the calculations, we just consider total moment equal to 0, clockwise and anti-clockwise. Anti-clockwise is positive. Okay, clockwise is the negative. But at the end, once you determine the angle of twist, you use this phi-sines rule. And not phi-sines rule. Phi-sines rule. Okay, after you get the answer. Okay. Okay. So generally, if you get angle of twist negative, right? So meaning that your thumb is going to be to the inside of the director to inwards, okay, to the side. Okay, if you get the radian, okay, negative, the value is negative. So meaning that your thumb should be direct to the inward of the shaft. Okay. Okay, so meaning that is to this side. Okay, it's the opposite. Okay, so let's see the example. I think that there's a one example, good examples showing that how to use the phi-sines rule. Okay, this is the example. The gear attached to the fixed and steel shaft, right? Is subjected to torques shown. The shear modulus of elasticity is 80 gigapascal. The shaft diameter is 40 millimeter. Determine the displacement of the point P. Where is the P? This one. Okay, displacement. Displacement is a distortions or deformation. The same meaning. Deflection of point P on gear A. Shaft turn freely within the bearing at beam. Okay. So if we calculate, okay. Right. If you look at here, we start from which point? 150. Okay. So this is this one. We start from this side. Okay, because this is a fixed point. Generally, we start from here, from point A, because that one is fixed point A. So based on the moment or equation of equilibriums, this one to the counterclockwise. So this one is clockwise, TAC. So we can get the same value, equal but opposite, right? Similarly, also this one from CD, this one A, B, C, right? So this is TCD. So just this one and this one. This direction, opposite TCD, right? Based on this one. Okay, similarly also D, this one, and this one. So if you get this one negative, meaning that your torsion is going to be opposite lah. Okay, the top, internal top. Okay, internal top is going to be opposite lah. So you have to correct this is value to not value, the arrow to the actual direction. Okay. Okay. Okay, so this one is you just determine based on the counterclockwise and clockwise. Okay, what you have to do is the displacement at point and the right. Okay, by sign convention right hand rules. Okay, so you can get here that TAC is to which one? This side, and then this side, and then this side, right? Okay. So this one is if you look at there is this one negative lah. This one this side lah. Okay, it's the same. Okay, right. Okay, and then you have to calculate angle of twist. Okay, angle of twist. So if you look at here, angle of twist is negative 0.212 radian. Okay, by using TLJG. Okay, phi is a negative. So right hand rule here, it will rotate clockwise. Okay, because it's negative. So meaning that to this direction. Okay. So it's inward. This is inward. Okay, the final. Okay. So that we get the answer lah. Okay, for the final because it's negative, right? Definitely is a clockwise now. I can say is a clockwise. Okay. This is another example, I think. The same. Okay. So just determines the angle of twist at NB. Right. Yeah. This is a fix. So you just using cut off section. This one cut. So you can get, see, this one is a positive. Yeah, this one 60 lah. This one negative 60, negative 90. Okay. Plus this one is 60, 60, 90. Okay. Okay, 90, negative 90. So it's positive. Okay. So this is the correct. So this side, and this side. Okay. So if you look at here that why is not moving? Okay. So we can get negative, positive, negative lah. Okay. And then we calculate. So we can get negative. So this is the clockwise. Okay. So meaning that this one by using right hand rules. So your hand, this one. Okay, to this side. Okay, the same. Okay. Is it clear? Okay, let's see. Now is what time? 9:25. Okay. So we break for 5 minutes if you want to go toilet. Okay. Or you want to have a drink before we finish for the power transmission. Okay, we see at 9:30. Okay. We start again at 9:30. We stop for the power transmission. Okay, we continue. Okay. So on the power transmissions, okay. So power transmissions, I think you know what is about the power transmission or transmission shaft lah. Okay. So generally we use to transmit the power to the speed of the rotation. Okay, so that is about the what is it the power transmissions. Okay, for example, to transmit power from the engine to the wheels. Okay. Okay. So power is defined as work performed per unit of times. Okay. For rotating shaft with torque, power P is a P equal to T omega. So this omega actually is a angular velocity. Okay. So difference in theta and also T. Theta I think is the angle. Okay. That is angle. Okay. Since one cycle is equal to 2 pi radians, so one cycle is around 360 degree lah. Okay, and F is I think the frequency. Okay, the frequency in hertz. Okay, if you still remember frequency uses in. So power 2 pi F the frequency and T is the what is it? The torque lah. Okay, T is the torque. Okay, so we can relate with the previous example actually. Okay, so for shaft design, okay, you still remember this one? So this actually the originals equations should be this one, right? Tau is this side, okay, and then this down this one. So tau equal to Tc over J. So we can calculate this T and substitute into this one. Okay. Okay, let's see the one example. okay, for the power transmission lah. Okay, and I think we have how many examples this one? 2, 3, 4 examples. Okay, and the rest I think you can read. Okay, example 1. Steel shaft AB shown is used to transmit 3750 watt from the motor, and which is attached. Which one? AB. This one. Okay. The shaft rotate omega angular of twist. Okay. Has allowable shear stress 100 megapascal. Okay, this one tau allowable. Okay, determine the required diameter of shaft to the nearest millimeter lah. So just remember that from the equation of P previous one, right? P omega P equal to P omega. Okay, so this one is equal to 3750 watt lah, because it's power, right? Okay, omega is, what is it, 100 rpm. So we have to change to radian per second. Okay, 175 per minute. Okay, so one rotation is equal to 2 pi 350, 2 pi divided by 1 revolution, 1 minute, because this one is 1 radian, right, per minute, right? Okay, 50 seconds. So you can get the answer. Okay, so please this is, you have to determine P divided by omega, so you can get the answer. Okay, so since we determine already T, it said what is the required of diameter. Of course C lah, we have to determine C. Okay, so from the equation, J equal to C equal to tau divided by tau allow. Okay, so we know this one, right? Okay, J we know. Okay, J, because this is a solid shaft. Okay, so we just J is equal to what equation lah, J? If you still remember, J for the solid shaft, okay, half pi T power of 1, right? Okay. So we can get, so just rearrange, okay, in term of C, so we can get C, okay, 2P divided by pi tau allow, okay, tau allow, okay, so you can get value of C and then convert into, okay, so that is the allowable diameter. So this is the solution. So you look at here that we use a power equation. Angular we change to the radian per second, and then T in term of P and omega. So this one J, right? This one equation for J. So just rearrange in term of C, so we can calculate. Okay. Any question about this power? I think other example is also similar. You can read. There's already have a what is it? The solution there. I already provide the solution. This is not homework, okay? Homework later I will give in the e-learning. So please read. I think I include the question about the power, if I remember. Okay, just like a previous. previous semester. Okay. Any questions? Any questions? Okay. So no, okay, thank you. If you have no questions, we stop here. Okay. Just read the other example. Okay, study other examples. Okay. This one is not the homework. Okay. And then I will upload the homework in the e-learnings. Okay, for chapter. Later, what chapter include for test two? Which one? Let me check. I forgot. Chapter 1, part 2. The introduction, if you still remember. And then I think is wait, uh, first chapter of this topic, materials, not materials, mechanic of materials. Chapter 1. What is it? Chapter 1? Introduction, concept of stress. I will prepare the question actually. Okay. So you can solve it by using method of section or method of join. I think also a shear stress. Shear stress, if I still remember. I don't remember. But mostly it's method of section and as well as let me check. I think it's shear stress for chapter 1. Okay. So a mechanic of material chapter 1. Mechanic of material chapter 1. Yes, this one. Part 2, mechanic of material. This topic lah, chapter 1, chapter 2. We have 3 chapters, right? So chapter 1. So this is covered CO4. And then another one is phase eutectic. Phase eutectic. Okay. You know solid solution phase eutectic? That one is another one. So meaning that we have 2 questions. Chapter 8 phase eutectic as well as chapter 1 part 2 mechanic of materials. So that is uh, the cover. This is the chapter that we cover for test. Yeah, mechanic of materials. Mechanic of material chapter 1 for test 1. Okay. For chapter 2 and chapter 3 we will cover for final. For final. Do not forget 17 January. Okay. That is for test 2. Okay, any more questions? Why I'm sharing? Okay, if you have no questions, for those who still not scan the QR code for the attendance, so please scan and thank you very much. We have finished already. So I will upload the homework as well as the project. Okay. Thank you very much.